Welcome to the new topic of the physics curriculum, which is uniform circular motion. This follows from our topic of projectiles. I've created a bit of a presentation to introduce you to the concepts of uniform circular motion. Okay, so a review of some of the things that we've learnt in previous classes. Speed is a scalar quantity and velocity is a vector quantity, and they are different things in physics. So speed refers to the magnitude, and you can see that in the example one with the orange car. The orange car's speed is 200 kilometers an hour. Now, with the car underneath, the white one, the velocity is written as 200 kilometers an hour to the left. Now, the white car also has a speed of 200 kilometers an hour, but with velocity being a vector quantity, it has both the magnitude and the direction. Now, when we refer to uniform circular motion, we'll be looking at acceleration as well, and acceleration is also a vector quantity with both magnitude and direction. I will now explain uniform circular motion from its definition. So if we consider that carriage on the Ferris wheel, the red one, traveling in an anti-clockwise direction, the speed of the carriage is not changing, however the directional component of the velocity is. So we can see when the carriage is in this location where my cursor is, the direction of travel is out here, and as it goes around, the direction changes. So we can see this more clearly with this example. So as that little man is moving around the circle, we can see his velocity direction is in the direction of the arrow. And what we can also notice about this is that the arrow is not changing in size. The magnitude is always the same. And what this means is there is no acceleration or deceleration in the direction of velocity. Now, since it's changing direction though, the velocity of the carriage is changing. That is because velocity has two components, which are the magnitude and direction. So if one of them changes, then the velocity changes. So in our case, the direction is changing, meaning the velocity changes. Now, by the definition of acceleration, a change in velocity indicates acceleration. Therefore, the carriage is accelerating. Now, we know that acceleration must be perpendicular to the velocity as the object is traveling at a constant speed. So the object is not increasing its magnitude of speed or decreasing, and that is, as a result, means that acceleration is perpendicular. Now, looking at these two diagrams, we can see in the first one on the left, the velocity direction is going out to the right here, and the acceleration towards the middle. Now we've got a F here that represents force, as force equals mass times acceleration. I'll come back to that in a minute. Now we've got this diagram here, where the direction of velocity is out tangential to the circle, and the force or acceleration component is towards the middle. As the acceleration does not change the speed of the object, and speed meaning the magnitude of this velocity, the acceleration must be in direction that is perpendicular to the velocity. So it is tangential to the circle. Now, if this particular Ferris wheel carriage did not have any acceleration whilst traveling in a circle, it would continue in a straight line. What the acceleration does, due to a force, is to bring it back, is to pull it back on its circular path. Now, this acceleration that continuously points inwards towards the center of the circle is known as centripetal acceleration. So we can see here that the acceleration is always towards the center of the circle. And we can also see that the magnitude of the acceleration is constant. Okay, previously I explained uniform circular motion from the definitions. Now I will explain it from Newton's laws. So Newton's first law states a moving body continues to move with constant velocity unless an external force acts upon it. And because the carriage is not moving in a straight line, because it is in a circle, there must be a force acting on it. Now, Newton's second law states that force equals mass times acceleration, and that suggests that the carriage has acceleration. The force in this case is provided by the arms of the Ferris wheel that connect the carriage to the central pivot point. Now, we use the Ferris wheel as one example, however, there are other examples of uniform circular motion. We have a vehicle travelling in a circle. Now, the centripetal force is due to the friction of the car's wheels. Now, that means that the car maintains its circular path due to the force provided by the friction of the wheels to keep it on that line. Another example is a bucket of water spun in a circle. Now, the tension acting in the string is the force that provides the centripetal force. Another example is the moon when it orbits Earth, or Earth when it orbits the sun. There is no direct physical contact between the two. However, it's the gravity acting on the moon that provides the centripetal force to keep it in a circular path. So we can have a look at an example of a car, and we can see that the friction force is the force that points towards the center of the circle, and the velocity is tangential to this force. We can have a look at this from another point of view, where the car has no physical contact with the center of the circle, yet it is traveling in that direction due to the friction of the tires, forcing the car inwards. Another example is the orbit of the Earth around the Sun. Now, gravity is actually providing the force that provides this centripetal acceleration, and that is shown there. So gravity is always constantly pulling the Earth towards the Sun, stopping it from flying in a straight line. Now, the velocity component is shown in that, shown with the red arrow. However, if we take away gravity, the direction of the red arrow is where the planet will fly if it wasn't for gravity. So they will continue in a straight line by Newton's first law. Now here I've provided a formula to calculate the magnitude of the acceleration if the speed and the radius of the path is known. I have not provided derivation for this at this stage, however, if you're interested, please let me know. I can go through it in class. So what we've got here is acceleration is equal to the velocity squared divided by the radius. However, we can notice that the velocity squared term, acceleration is proportional to velocity squared. So meaning the greater the velocity, the greater the acceleration. Also, the radius is inversely proportional to the acceleration. So the smaller the radius for the same speed will have a greater acceleration. Another equation here which relates the period to the velocity and the radius. So the period of the rotation is equal to 2 pi r divided by velocity. Now we recognize 2 pi r as the distance or circumference around a circle, and if you divide distance by velocity, you get time as one of the physics equations. So it's simply just converting one of those equations to application of uniform circular motion. Now what I've provided here is animation for you to investigate the effects of the size of the centripetal force. So you can play with the variables of mass, velocity, and the radius, and notice the effects that they have on the centripetal force. In my next video, I'll provide you with some examples on how to use the equations. Okay, so I'm going to go through a couple of example questions based on uniform circular motion. I'll present these questions at the bottom of the video. Question 1. A car is travelling around a circular racetrack at 100 kilometers an hour, with a racetrack having a radius of 30 meters. A. Find the centripetal acceleration of the car. So our first step in this example is to convert 100 kilometers an hour into the standard units, which is meters per second. So we can write kilometers per hour to meters per second. Now, to get kilometers per hour to kilometers per minute, we divide by 60. That gives us kilometers per minute. Then to get kilometers per second, we divide by 60 again. Now, our final step, to get meters per second, we times by 1,000. So we get meters per second. Now, with our original units of 100 kilometers an hour, converting that to meters per second using a calculator, we get V equals 27.77 meters per second. Okay, so that's the first step. We know V. Now, for centripetal acceleration, we know the formula of acceleration is equal to V squared over R, with R being our radius of 30 meters. So we just substitute these values into the equation. So V is 27.77, R is 30, and using a calculator again, we get the value of 25.72 meters per second squared towards the center of the track. Now, we must remember that acceleration is a vector quantity, and that's why we have the direction nominated as well. Okay, let's move to part B. If the car has a mass of 800 kilograms, find the force that is exerted by the tires to maintain the acceleration. Now, the tires are the component of the car that provides that force, so that's what we're looking for, and we can use Newton's law for that. So F equals ma. Now, we have just found A, and we know m given in this part B, so it's a matter of substituting the values. So the mass is 800, the acceleration is 25.72, our result is 20.58 kilonewtons. This is also a vector quantity, so we must write the direction, which is towards the center of the racetrack. Okay. Now, part C. Find the period of the car. Find the period of the car in its circular path. In this example, is how long it takes to complete one lap. So we know our formula for the period is 2 pi r. That represents the circumference of the circle, or the distance of the racetrack, one lap, divided by the velocity, the magnitude of velocity. So that's how fast it is going. Now this makes sense, because we are working out the distance divided by the speed, giving you the time around the track. So we can just substitute the values that we know. So radius being 30, this velocity value being the converted value of the velocity from 100 kilometers an hour, which is 27.77. Now, using our calculator, 188.5 over 27.77, which is equal to 6.78 seconds. Okay, we've got a second question here. It's a bit hard to read the question, but it will be at the bottom of the video if you can't read it. An object of mass 2 kilograms is rotated in a horizontal circle on a cord of length 1 meter. The cord will break when the tension in it becomes 500 newtons. The speed of rotation is gradually increased from 0. A. Find the speed at which the cord breaks. Okay, so I usually start questions like this with a diagram, and with the diagram you can see the concept and what is actually happening and what you have to work out. So, in a horizontal plane, the object is rotating around, with the center being the radius to the edge of the circle. So, we know what the radius was 1 meter. So I'm just going to write an R for radius. An object is on the M end, and the object has mass 2 kilograms. With the velocity of the object being perpendicular to the acceleration as it is in a uniform circular motion. Okay, so what do we know? We know the force, the mass, and we need to find the acceleration, so we can start with that. So we know the formula from Newton's law, being force equals mass times acceleration. Now, we need to find the acceleration, so we can rearrange the equation. So acceleration equals force divided by mass. Now, we know the force is 500 newtons, and the mass is 2 kilograms. So we get an acceleration equal to 250 standard units, meters per second squared. Now, what we need to find is the speed. So we can use the formula for uniform circular motion, being acceleration is equal to velocity squared over the radius. And we know those values. And we know we need to find the value, the speed. We need to find the speed, which is related to this term here, so we can rearrange the equation. So v squared equals a times the radius, and v is equal to acceleration that we worked out before times the radius. So we can substitute these values, and we get 250 times radius, which is 1, which gives us an answer 15.8 meters per second. Tangential to the path of travel, as this is a vector quantity. So what this tells us, find the speed at which the cord breaks. So the rotation of the mass on the cord increases in speed until it reaches 15, where it's still not broken, and it keeps going a little bit faster, and at 15.8 meters per second, tangential to the path of travel, the cord breaks. The question is looking for the speed. We do know the direction of the velocity, so we can add that in as extra information.